So in case you haven't already thought of it like this, whenever you look at matter, whenever you look at your hand or look at the desk or look at your pencil, I want you to think about that matter being made up of atoms. Now, matter can actually then be in one of three, what we say, physical phases. And you're probably, I know you're already familiar with this. Matter can be in its solid state, matter can be in its liquid state, and matter can be in its gaseous state. Now, we're going to talk more about this, but probably you would tell me if I want to go what I say from left to right, from solid to liquid to gas, what am I going to do? I'm going to add heat. Okay, add heat. I can heat something up and make it change its physical phases. We'll kind of keep that in mind, I think, because that's helpful. So down here, I like these pictures also. Here is matter in its solid state. Now the matter we're dealing with, these cute little Mickey Mouse molecules, are actually H2O. So we have an oxygen in the middle, and we have two hydrogens kind of scooting out like that. And actually, at one point in the class, we're going to talk about why do the hydrogens scatter like that, and there actually is a reason for that. But these are cute little water molecules in here, and notice a few things. Notice that in their solid state, they're close together. I guess that's the biggest thing to notice. And let me see if you can tell it. No, you can't tell it, but they're stuck together and they have motion, but they move very little. So little movement. Okay. I don't know, you could say there's little movement because they are just so cold. Or you could say that they're little movement because they are actually, they're very much stuck together. There's like this webbing we call intermolecular bonds connecting those different water molecules. So over here now, the next one, we have water in its liquid state. And hopefully if you compare these two, you can see that the water in its liquid state is, let's see, how do I say? It's more disorganized, okay, and it is floating around. There's actually more space between them. It's less ordered and there's more space. And if I were to be able to look at that webbing, those intermolecular bonds, there's definitely less intermolecular bonding. And there is, according to movement, there is more movement. And again, you probably can't really see this movement unless you're looking at it at a molecular, the molecule or the atomic level. So of course over here, then to the far right, we have our gases. I love gases. Gases are my favorite physical phase. So right off the bat, you can see that, well, a few things. Notice that, as it turns out, if a gas is behaving what we say ideally, there are no bonds in between them. There's none of that webbing, none of the, what we call intermolecular bonds. The other thing is I love gases because they have a mind of their own. I don't know if you can kind of see this little wispiness here, but this is trying to show you motion. So they have a lot of motion. Okay. Gases are great. They basically, what we say, they'll take on the volume of the container you give them, and they'll take on the shape of the container that you put them in. I think that is so cool. So actually, along those lines, I have this little table here. So starting clear at the left are solids. What we would say with regard to size and shape. Well, solids are stuck with the size and shape that they have. Okay, there's no blobbing around, right? Okay. What's the sort of webbing, what's the intermolecular bonds that they have between the solid particles, whether it's water particles or aluminum particles, they have what we say a high degree of those intermolecular bonds. Okay. How much kinetic energy do they have? Well, that's the motion part. Kinetic energy is energy associated with motion. So if they don't have much motion, they don't have much kinetic energy. Okay, so that last column is motion. So what would we say about liquids? Well, a liquid actually, the size is stuck, okay, but liquids take on the shape of their containers. So the shape of liquids are what we say indefinite. See how that works? We have an indefinite shape. Okay, they take on the shape of their container. The next two, how much intermolecular bonds and how much kinetic energy we have, well, I just put moderate. Okay, so we have kind of in between solid and gases. They have some intermolecular bonds, some of those webbing connections, and they have more motion or kinetic energy than solids, but not as much as gases, okay? So then we get to my favorite physical phase. Should be like, one of these questions should be like, what's Mrs. Snipes' favorite physical phase? And then hopefully everybody would say gases. So gases have no intermolecular bonds, nothing to keep them connected to each other. I guess that's one thing I don't like about gases. But aside from that, they take on the shape and the volume of their container. Is that not cool or what? So their size is indefinite. They take on the volume of their container, and their shape is indefinite because they take on the shape of their container. And that's kind of almost like, let's say, peer pressure, but no. Anyway, I still like gases. Gases, we say they basically are not connected to each other, so their degree of intermolecular bonding is none. And then we say they have a lot of motion, so they have a high degree of kinetic energy. Is that not cool or what? What's not to love about gases? So this next, see if it'll go on. Oh, good. So we'll be, we're going to talk more about that webbing, that thing that sticks particles together. That's called intermolecular bonds, okay? Intermolecular forces or intermolecular bonds, right? So those intermolecular bonds, we're going to talk more about what an ion is, but it can connect two ions together. It can connect two molecules together, intermolecular bonds, and intermolecular bonds are kind of like interstates. They connect states, intermolecular bonds. They can connect molecules and ions. So, and I have this little video here for you. I like it. Let's see if it plays for us. Okay, so you can see the motion. Now I'm going to see if I can get this to repeat. Yeah. Okay, so from left to right we have solid, liquid, and gas. Is this not a cool video or what? And who's, like those gases on the end there? I wonder if this will let me, no, I think it'll freeze. But I'm just going to put, I love those gases. Okay, so let's see, how do I go on to the next slide? Oops. Let's try this. Okay. So just a little more then. This is a figure from your textbook, and it kind of summarizes what we've been talking about the three physical phases. So here in the first column, you see the three physical phases. You see solid, liquid, and gas. And here we see what is the spacing. Gases are close together. Sorry, gases. Oh my goodness. Solids are the closest together. Usually. Water's a little bit different. Water kind of fluffs out when it transitions from a liquid to a solid. We talk more about that later. Liquids are pretty close together. Usually there's a little more spacing for liquids between liquid particles or molecules than it's solid state. And gases are way far apart. The shape of a solid is definite. It's stuck. The shape of a liquid is not definite. The shape of a gas is not definite. The volume of a solid is definite. The volume of a liquid is definite. The volume of a gas is indefinite, rebels that they are. Okay. Compressibility deals with squeezing. Can you squeeze it and make it smaller? Solids and liquids generally no. If you apply pressure, something else might happen, but they don't squeeze together. Gases you can compress. Okay, gases, have you ever heard of compressed gas, compressed air? Okay, so gases you can squeeze down into a container, which is kind of a fun sort of thing too. Gases are great. Let's see. See if this video plays for us. Oops. Does that mean no? Well, I'll work on the video. Oh, there it goes.
Matter changes. Atoms and molecules are in constant motion. Heat increases this motion. The amount of motion dictates how well atoms and molecules can hold on to each other. The less motion there is, the better the hold, and the more solid the matter. When liquid water is cold enough, its molecules arrange in a particular structure and turn to ice. When heated, the vigorous motion of liquid water molecules separates them from one another, and they become an invisible gas.
Is that not cool or what? All right. So I'll just go ahead and put this slide up there. You have this in your notes, and this is the first official assignment from your textbook. Let me know if you have any questions.